backplanes that have normally been used for the LCD industry, and now they're using them for this new emerging display technology. And so it really sort of sets the plate nicely for what PlasticLogic wants to do. What PlasticLogic wants to do is make a display which is flexible, and I actually have a real one here. So I will have it. I'll be around a little longer. So if people want to take a look, please stop by, see me at the stage, because you will see that this is actually a flexible display. So we have a prototype. We've got it. This is what we envision making. So how do we go about doing it? It's been built over 10 years. It's probably expanded now to 15 years of plastic electronic innovation here in the Cambridge area. We have a team of over 55 people. So we have a good group of people that are ready to tackle this task. We're working currently on our Series C round of funding, which was over $28 million. That had new investment partners, Oak Investments, Intel came in at that point, BASF, which was, both of those have been great investors for us. And also we have the continued support of Polytechnics, and obviously Amadeus has been a great support system for us. So this is the display technology that has been used already in those Sony products and the other electronic reader products. And what it simply is an electrophoretic display where you have black electrodes, the white and the black particles moved to the top surface. And therefore you can grab a black and white image. Now these things don't change, the position of the particles don't change when you turn off the voltage, therefore it becomes a bistable effect. It only changes when you actually update the image, so you can update the image and leave it there. It also can do grayscales simply by the relative number of black and white particles that are on the top surface. So it's a very sort of exciting medium. E is by far the sort of front runner in this sort of display effect, but there are loads of other companies that are either emerging or have emerged. Bridgestone and Cytex are the most notable ones there under the pigmented type displays. And then there's also what we call other sort of bistable effects, which I think our technology will be well suited for. We haven't quite worked with all these people yet, but this is the type of area where I think our technology is the most applicable for. So it's pretty simple. You just take the electronic ink or the electronic display effect that ink now sells, and you can just simply laminate it onto your flexible backplane, which we made. So you have your flexible backplane, which is display technology, so exciting. The first thing is any sort of new flexible display, you wanted to make sure you made it in a manufacturing way. Always, so the mantra of sort of high volume manufacturing is kept in our minds the entire time when we were developing the process. And so I'll talk a little bit more about how we did that, how we made sure that any sort of innovations that we made were applicable not only in the lab, but also in a high volume LCD. Onto the flexible backplane, the biggest problem is that the substrate for the surfaces that you're working with is stored. And that causes loads of problems for all the current LCD manufacturers, and therefore that's why it hasn't been done yet. And so we really needed a way to be able to make large area displays and to be able to cope with distortion. That's what we've done. Finally, performance is always going to be a primary issue. So we had to make sure that we were dealing with switching speeds that were attractive or met the electronic paper requirements. And then there was also some other innovations. Actually, after you got that switching or the switching requirement under control, other innovations that actually improved the front of screen performance on the displays. I'll talk about those as well. So the first one is the ability to manufacture. And as Herman already mentioned, it required us to develop very simple processes that moved very quickly, so we didn't have to buy those machines to balance the line. So that was always kept in mind as we were developing. Control starts from the bottom, so we start with what is the cheapest substrate and see if we can sort of process on that. The biggest problem with the PET is that once you sort of get above 100 degrees C, the PET really distorts very severely and it becomes very difficult to work with. So we had to make sure all of our processing occurred below that temperature Finally, is we wanted to reduce the material cost even further as you work up and add layers onto your backplane. And how we did this is, whenever possible, we would simply work with commodity materials. We always try those first and try to make those work. When commodity materials, when you actually had those special materials, those expensive materials, you put them down in an additive way so you weren't wasting, you weren't sort of throwing them down the drain. So that's how we come across, or come to making a fairly low-cost, flexible backplane. And to kind of show you that we got it somewhat under control, we have our prototype line here in Cambridge, where we currently work on 14-inch panels. That's what we're capable of handling. We fabricate displays in 2 shifts daily, the day shift and the night shift. And all the equipment that you see here, and all the equipment in the prototype line, is currently sort of semi-automated. There's some cassette loading that we do. But the important bit is that a lot of displays of large areas, and actually handling that distortion that I was talking about. The first thing that we decided to do is I mean, we're using PET, but there's things you can do with PET. You can heat treat the PET to ensure that the distortion that you get as it goes through the process is as limited as possible. Any sort of distortion, it's going to be too much to cope with using standard sort of photolit techniques. So there's other games you can play. You can change the masks you use and the patterning steps to allow a little bit of alignment tolerance in those patterning steps. However, even when you do all that stuff, ultimately you can't make a large area and flexible display on a distorted panel unless you have some sort of direct bright technology. You have to be able to compensate for the distortion as the panel moves through the process. And so that's, I think, really what we were able to come up with, and a real key to our technology. And just to show you that how exciting this is for PlasticLogic, you can see one of our displays there in the background. It's an A5, 100 pixels per inch display. And it's, you have the Sony products there and the IREX product as well. And that's just to show you what's currently in the market. I mean, obviously, the glass displays can't get bigger because they don't deal. They're limited simply because they're dealing with a lot of photolit steps that actually they can't cope with distortion. They can't do it. So this graph here shows you that where our technology excels, and that's actually making larger area displays. Now, the distortion doesn't simply affect the area, it also affects the resolution. As you try to make things more and more resolved, which is required for an actual product, or distortion becomes a bigger and bigger problem. So again, not only will those mass-based process have a problem with dealing with large areas, but they're also going to have a hard time getting the 150 pixels per inch or above that we believe is required to make an electronic paper product. And so this is a demonstration of our technology. You can see a slight improvement in sort of the contrast and the sharpness of the image as you increase the resolution. And that's something that we're working on very hard at the moment. So the last task is the performance. And I'm sure not many of you here have seen many of these graphs. These are transistor curves. And rest assured these are very well behaved transistors. These are transistors that normally come from a process line. The sort of figure of merit that a lot of people mention is the mobility. That right now is around 0.02 centimeters squared per volt second. Now, as Herman said, the amorphous silicon is a little bit higher, and there are polymers that can respond, or organic semiconductors that can work at a higher mobility. However, for the electronic paper products that we're making right now, it's important to mention that we don't really need more mobility than that. We can run an A5 size display with up to 16 gray levels using transistors that look like this. So that was a big sort of step in our at PlasticLogic about feet to run the paper display. Let's start making some displays and just to show you how well a flexible backplane produced at PlasticLogic and hope an image like that shows you that the performance that we're getting is up to par. So now comes to those other innovations that I think people, at least the engineers at PlasticLogic, were sort of very impressed with how much they improved the front of screen performance when you look at a flexible or any sort of display effect. So when we were first making our panels or our displays, we would put the display effect right on top of our bus lines. And as you can see there, in the image on your left, is the little black lines that are going across the display. And that was simply because the bus lines were shielding the voltages that the display effect needed to run properly. So what did we do? We actually just put an inner layer of dielectric on top of those bus lines, and then offset the electrode on top of that, giving us a high aperture ratio structure. And you can just see how a simple effect like that makes such a dramatic effect to the front of screen performance and actually gets you closer to an actual product. Same thing for like sort of semiconductor patterning. When you first make the displays and you start driving, you look at them and they're big gray, especially when you're trying to drive the really high resolution images, they just don't look right. It's very washed out. You realize that there's leakage paths from all the different pixels to each other. And so you figure out how to isolate that semiconductor so it's only in the pixel area that's required. And all of a sudden, you have a very sort of gray display turning into a very crisp, high contrast display that is required for the market. And so it's those little innovations that were also required as well as worrying about the switching speed, which was also important. This is a nice slide, at least for the people who have followed the PlasticLogic story over the past 5 years or 6 years that we've been around. And it just shows you how we have evolved. If I was giving this talk 2 years ago, I would have came with a 2-inch display that was 50 pixels per inch. And you can recognize the face on that display there. And that was back in December 2000. Later on, in the next year, 2005, about midway through, we decided to show that we could make a higher resolution display. But of course, we had to shrink it. Because now we're making a 1-inch, 100 pixels per inch display, and that was really exciting at the time as well. At the same time, we actually increased the size of the display, and this time making a 10-inch display. But of course, the resolution was only 10 pixels per inch. So that was also exciting at the time. And of course, we tried to push the technology a little bit, try to get the higher resolution. We're actually able to make a 300 pixels per inch display at the tail end of 205. But I think the reason why there's been so much excitement about PlasticLogic recently is about what happened in December of 2005. So that's a year ago, obviously. This is that came off the line, 10-inch, 100 pixels per inch display. Which I think of most people, when you're handling a display, you realize it is electronic paper. We've got it, we made it. And I think this is where all the excitement is happening. So we spent the last year trying to figure out what the best way is to make money off that. Herman allowed me to show this slide, so I'm very grateful for him. And this is just to show you the flexibility that our displays have. And some of the other attributes. I mean, you can see how thin the display is, and compare that to some of the e-reader products that are currently on the market. It's quite attractive. Here it is, it's being updated. You can see invented. So the shoe gets polished. Try doing that to your glass-based display. The robustness is actually one of the biggest selling points for this technology. You can drop this, you can carry it around. It's going to be okay. I forgot that. I don't know if so this is the other advantage. It's very light. Here's compared to a newspaper, but also relative to a glass-based display. You can make the argument that our displays will be much lighter. So that's what happened over the past year, and the excitement that was at PlasticLogic and what people were seeing. We wanted to go down to see what other people had in mind, what kind of products could be made with this technology. So we went down to a design school in London, Central St. Martin's, and allowed second-year design students to just take a look at our technology and see what they would do with it, where would they put it. And you can see some very sort of unique ideas that came from these people. You have an electronic music score, which would save a lot of musicians up with a lot of hassle. It's several different varieties of electronic books that were presented. The one on the bottom there is a snap medical stick, where you have a tempered steel that you put a small display on it. You can just sort of snap onto your wrist, and the display would update all your vital details as your hospital stay continues. So a lot of very exciting ideas, and it's really sort of good for people at PlasticLogic to see what other people had envisioned for this technology. But ultimately, I think there will be some sort of electronic book, electronic paper application that will be the first to hit the bookshop and the stores, if you will. So just keep abreast of the story, because it's moving quickly, and I thank you for your attention. That's all I have. Color. Color. There's two ways you can sort of do color. One is to actually wait for the electronic display effect suppliers to make color electrophoretic displays, and of course we're waiting for that development. The second is actually this sort of color filter. We've worked with it a bit, but I think that the first thing is to take the black and white part before we worry about color. Light expectancy. We measure sort of light. The transistors themselves we haven't been able to really kill those. So in terms of that's a big start when we're talking about organic based transistors. So the lifetime of the product would be sort of any several years. Power consumption, I don't really have a number for that, but it was, you look at this display. Yeah, well, you look at this display here, and I think we kind of overloaded it with power, because we didn't really know the power consumption at that point. All the calculations that were done after that show that it's actually very low power consumption, and all the advantages